Optimization problems. How can we maximize or minimize a particular region inhibited by a secondary region? Here we can examine this by using our knowledge of relative extrema. The goal is to one, understand what the problem is asking, identify two types of equations. One equation would be a primary equation, and then the other would be a secondary equation. The primary equation is the equation that you want to maximize or minimize. The secondary equation is where you would glean necessary information to inject into the equation to hopefully maximize or minimize the area or the volume or whatever the question is asking. From there, you want to use either the first derivative test or the second derivative test to determine at a particular point that the region is set to be maximized or minimized. And then hopefully from there we should be able to solve the problem. Let's take just some basic problems and consider those and just work our way up. Since the product is 185 and the sum is a minimum, so if it's the product, let's let x and y be the two numbers. So x times y is 185. And then it says the sum is what we want to minimize, so the sum would be x plus y. Now notice from this first part that we can pull out from here that y is equal to 185 divided by x. So if that's the case, then s can be written as x plus this y part, which is 185 over x. To minimize s being the primary equation, x times y equal to 185 is the secondary equation. To minimize s, basically we just take the first derivative, apply the first derivative test, and hopefully we should get our answer. So here this implies that s prime is equal to 1. Think about this as being 185 times x to the negative 1, so the derivative becomes negative 185 times x to the negative 2, or minus 185 over x squared. And if we set the second derivative equal to 0, this implies that we have, just combining these two terms, this gives us x squared minus 185 all over x squared is equal to 0. Now from there, if you multiply both sides by x squared and then solve for x in the numerator, you get x equal to plus or minus the square root of 185. This implies that x squared minus 185 is equal to 0. And here, x comes out to be the square root of 185. It says find two positive numbers. So the negative square root of 185 we discard. So we partition the number line based on this number here, the square root of 185, and we're testing s prime, testing its sign. We can use this. So take a number less than the square root of 185. Let's take 1. We get negative. Take a number bigger than that. Say, for example, if you take 100, plug it there, we get positive. So we have a minimum. At x equal to the square root of 185. Well, we need the value of y. So y is said to be 185 all over x. So that's 185 divided by the square root of 185. Now this is 185 times the square root of 185. If we rationalize our denominator, And this is all over 185, and so we get the square root of 185. So the minimum is at x equal to the square root of 185, and y is equal to the square root of 185. This next one, very similar. The product of two numbers, let's say that's x times y, is 147. And then it says the sum of the first number, let's say the first number is x, plus 3 times the second number is a minimum. So we call this S, or you can call it capital M or M-I-N, for minimum. It doesn't matter. It's some kind of sum. How about that? So from the first equation, the secondary equation, y is equal to 147 over x. So we get here, this special sum is x plus 3 times 147 over x. So this gives us x plus 441 over x. We take its derivative, so we have s prime is equal to 1 minus 441 over x squared. If we set this guy equal to 0, let's simplify this, if you will. This is x squared minus 441 over x squared. So s prime set to equal to 0 implies that x squared minus 441 is equal to 0. That is, x is equal to the square root of 441. And just double check. It looks like a familiar number, 21. So now we partition the number line based on this number, 21, and we're checking s prime. So take a number less than 21, plug it here, we get negative. Take a number bigger than 21, plug it there, and the bottom is always positive, so we get positive. So we have a minimum at x equal to 21. But what about y? Y was the 147 over 21, and that's 7. So we have a minimum at x equal to 21 and y is equal to 7. Moving right along, a farmer plans to fence a rectangular pasture adjacent to a river. So one side of the parameter is not needed. The pasture must contain 245,000 square meters in order to provide enough grass for the yard. No fencing is needed along the river. Well, good. What dimensions will require the least amount of fencing? So it tells us the area. That is that x times y is equal to 245,000 meters. The parameter is what we're aiming for, so this is going to be x plus 2y. So what dimensions will require the least amount of fencing? Well, let's see. So we want to minimize the parameter. All right. Well, notice from here that we can glean there that y is equal to 245,000 divided by x. You kind of see the pattern these problems tend to take on. We use up all the space we can. So P is equal to x plus here 2 times y, and y is the 245,000 all over x. This is x plus 490,000 all over x. So P prime is 1 minus 490,000 over x squared. So this is x squared minus 490,000 over x squared. Set that equal to 0, and we solve. We get x is equal to the square root of 490,000, and I need to work that out. I was thinking 700, but I tell you, my mind has been playing tricks on me today. So that's meters. So we use the first derivative test on 700. We're testing P prime, and we can use this P prime here. Take a number less than 700 from 0 to 700 because we're talking about something that's real. We're going to get negative. Take a number bigger than 700, we get positive. So indeed, we have a minimum. Minimum at x equal to 700 meters. Now y is that 245,000 divided by x divided by 700. That gives us 350 meters. Right? So this is our minimum. Y is 350 meters, and x is 700 meters. A Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Find the dimensions of a normal window of maximum area when the total parameter is 16 feet. As one of my favorite deacons would say, oh boy. Well, let's first build the parameter of the rectangle, and no need to include this side of the rectangle because that side will be included for the semicircle. So this is going to be x plus 2y. Now so this first parameter is the x plus 2y. To build the parameter for a circle, we call that the circumference. And here is going to be half of it. So the circumference formula is 2 pi r. So this is 2 pi, and r is said to be x over 2. It's going to be divided by 2. So here, that gives us pi times x divided by 2. So this is our parameter. Now what about the area? Why do you need the area? You want to maximize the area. So here, the area for the circle is going to be pi r squared divided by 2. This is pi r squared, where r is x over 2 to be squared. There's only half of it, so it's divided by 2 for the circle. And then the area for the rectangle is x times 1. Now, let's put everything together. So it tells us that the parameter is 16. So we have x plus 2y plus pi x over 2 is equal to 16. Now, and then we have the area, the total area is going to be x times y plus this pi times x squared divided by 4 divided by 2. So this is pi x squared over 4 times 2. We get 8. Now from here I want to be able to solve for this y, plug y in over there. So let's see. So we have 2y is equal to 16 minus x minus pi x over 2. And so y, let's go this way. The Three Stooges. So y is equal to, let's divide through by 2. So we get 8 minus x over 2 minus pi x over 4. So now the area is x times that y. Mama, there goes that man. Plus pi x squared divided by 8. So let's see, the area is 8x minus x squared over 2 minus pi x squared over 4 plus pi x squared over 8. So here the area, do a little simplification if we can. Combine these two guys. Make this 2 pi x squared divided by 8. And so negative 2 plus a 1, this is the 2. So this becomes negative pi x squared over 8. Combine these two guys, right? So now we take the derivative. A prime, oh boy, is equal to 8 minus 2x over 2 is just x minus 2 pi x divided by 8. 2 pi x divided by 8 is just pi x over 4. Okay. Set this equal to 0. We need to do some simplifying on it still. So this is a prime is equal to 32 minus 4x minus pi x all over 4. Set that equal to 0 now. So this implies that we have 32. Can I just go ahead and just go to it as equal to 4x plus pi x, right? And that is, this is 32 is equal to x times 4 plus pi. So we get x is equal to 32 over 4 plus pi. Not a good plus. And this is in feet. So we apply the first derivative test. At that point, 32 over 4 plus pi. We investigate a prime. We plug in that where? We're going to plug it here. Now you plug in x, some value for x less than this number, there and there to see what sign you get. And it has to be greater than 0. You will get positive. Take a number bigger than that number there and plug it in, and you will get negative. And so we have a maximum at x equal to 32 over 4 plus pi. What's y? Y is equal to, well, we had figured that out here. We'll plug that information in. So that's 8 minus the x. I'm going to write it a little bit different, help myself out. This is 8 minus x times parentheses 1/2 plus pi over 4. So you can write this is 8 minus x times 2 plus pi over 4. Now let's plug in x to equal to 32 over 4 plus pi. Times 2 plus pi all over 4. This is 8 minus 32 divided by 4 is an 8 over 4 plus pi times 2 plus pi. Simplify that. So this is 8 minus, this is 16. Be careful with that negative sign. So plus 8 pi over 4 plus pi. And so y is this 8 times 4 plus pi minus 16 minus 8 pi all over 4 plus pi. So we get 32 plus 8 pi minus 16 minus 8 pi all over, too much, 4 plus pi. The 8 pi's cancel. We get 16 over 4 plus pi feet. So the maximum is at x equal to 32 over 4 plus pi feet, and y is equal to 16 over 4 plus pi feet. Alrighty? Okay. Let's look at some more. Number 22, a rectangle is bounded by the x and y axis and the graph of y equal to 6 minus x over 2. What length and width should the rectangle have so that its area is a maximum? So this is number 22. So let's see. Here You want to maximize the area of the rectangle, so the area is x times y, and y is given there to be 6 minus x over 2. We want to maximize the area of the rectangle. So let's simplify this. This is 6x minus x squared over 2. We find a prime, and if you want to, you can write this as 3x minus x squared over 2. So then our derivative is 3 minus x. That's pretty nice. So we set that equal to 0. This implies that x is equal to 3. So if x is equal to 3, partition the number line based on 3, and we're investigating a prime. A prime is this. So take a number less than 3 and you plug it there. And here we get positive. Take a number bigger than 3, you plug it in. Here you get negative. And so we have a maximum at x equal to 3. If x is equal to 3, y is equal to, they give us the equation for y. So y is equal to 6 minus x over 2. I think I got that right. This is 6 minus 3 over 2. So we get 3/2. And there was no units for the dimensions there. And so here, according to the first derivative test, we have a maximum at x equal 3, y equal to 3/2. The last one that I will do in this section. A rectangle is bounded by the x-axis and the semicircle. What length and width should the rectangle have so that its area is a maximum? The same idea from the previous problem, actually. So here the area for the rectangle is going to be x times y. So the area is equal to x, and y is given there as the square root of 25 minus x squared. So to maximize the area, we need to find the first derivative. So a prime is equal to the derivative of the first, which is 1, times the second, plus the first times the derivative of the second. Well, actually, I did need that parentheses. So this is 1/2 times 25 minus x squared to the negative 1/2 times the derivative of the inside, which is just negative 2x. Simplify like Superfly. This is minus, the 2's cancel. This is x squared over the square root 25 minus x squared. So a prime, we combine these two fractions, that gives us 25 minus x squared minus x squared all over the square root of 25 minus x squared. So this is 25 minus 2x squared divided by the square root of 25 minus x squared. Now if you set a prime equal to 0, this implies that we have 25 minus 2x squared all over the square root of 25 minus x squared is equal to 0. And this implies that we have 25 minus 2x squared equal to 0. This implies that we have x equal to 25 divided by 2. X squared, that is equal to 25 over 2. That is, x is equal to, we're looking for positive numbers. We have a real thing here, so this is the square root 25 over 2. 5 over the square root of 2. So now we use the first derivative test, considering a prime. The pivot point is 5 over the square root of 2. Look at a number less than that for a prime. Take a number less than 5 over the square root of 2. Plug it in here, and you will get a positive value. Take a number bigger than 5 over the square root of 2 and plug it in for x, and you will get a negative value. And so that means that we have a maximum at x equal to 5 over the square root of 2. Now what's y? Well, y is given by the semicircle, the square root of 25 minus x squared. So this is the square root of 25 minus 5 over the square root of 2. That to be squared. So this is the square root of 25 minus 25 over 2. So we get 50 minus 25 is the square root of 25 over 2. And that gives us 5 over the square root of 2. Let's see. They're the same. The square root of 25 minus x squared. Let's see. This is the same as 5 times the square root of 2 over 2. So a number that I'm looking for is a 5 times the square root of 2. That's weird. Let's see. So this value here was x squared equal to 25 divided by 2. We took the square root of that, and that gave us 5 over the square root of 2. And that's 5 times the square root of 2 divided by 2, which is that number. So we take x to be that, plug it in for y. Okay, so this is 25 times 2 is 50 minus 25. So that's 25 over 2. And so this is what I'm getting. It's interesting. if I'm off, I'm probably off somewhere. A number that it looks to me that we ought to be looking at 5 times the square root of 2. And I could be sleepy, in which I am. Let me think about it. If here what I have is x equal to 5 over the square root of 2. We got that there. And then we took the value for y. If I got the same numbers, this rectangle wouldn't be a rectangle, it would be a square. And then we plugged in here x to be 5 over the square root of 2. That gave us 25 over 2. I have maximum at this and y equal to, I'm getting the same thing, I don't know why. I got something different earlier. If I can think of it, I will come back and let you know, but I do question this guy right here. Thank you. Sorry.